Hello everyone, class 12th topic is mechanism of electrophilic substitution reactions of haloarene. In previous video we have understood haloarenes are able to show electrophilic substitution reactions. Their ortho and para hydrogens are getting substituted by stronger electrophiles. Now let's understand mechanism. Mechanism is of three steps. What are those steps? Let's write down. Step number 1 will be generation of electrophile. Our chemicals will create electrophile. Second step will be attack of electrophile on benzene ring. What are electrophiles which want electrons? Benzene rings are best source for electrons because benzene ring contains pi electron. So next step will be the electrophile generated in first step will attack on benzene ring for electron. Due to that attack, carbocation will generate. So this step is also known as generation of carbocation. And third step will be the last step, loss of proton, H positive. In second step, due to generation of carbocation, benzene ring will become unstable because it will lose its aromatic character. So to rearrange, to regain that aromatic character, it will lose a proton and final product will be generated. So these are the three steps we have in the mechanism. Now please note down, second step will be slowest step. That's why it is speed deciding step. Speed deciding step, or we can call it rate determining step. Overall speed of the reaction will be decided by second step because this is the slowest step here. Now one by one, let's understand all the steps. First, generation of electrophile. Now we know electrophilic substitution reactions are of these types: nitration, sulfonation, halogenation, alkylation, and acetylation. In previous videos, we have done these electrophilic substitution reactions. Now we know what is the meaning of nitration. During nitration, what will happen? We know. Sulfonation, what will happen? We know. Now, for all these 5 electrophilic substitution reactions, I am going to write the first step of the mechanism, generation of electrophile. Look in nitration how electrophiles are generated which will attack on a benzene ring. We know in nitration which chemicals we are using: concentrated HNO3 and concentrated H2SO4. These are the two chemicals we are using for nitration. Now understand, this mixture will create how electrophile. HNO3. This is the bonding in HNO3. Nitrogen is making 4 bonds, so plus 1 charge. Oxygen is there. And sulfuric acid, I will write as it is because I don't need open form of this sulfuric acid. Out of nitric acid and sulfuric acid is a stronger acid. So in front of stronger acid, nitric acid itself will work as a base. Means stronger acid will provide H positive and weaker acid, which you can call base, will accept that H positive. H positive is an electrophile, so that's why it requires electron. It will attack on an oxygen for a lone pair of electron, and a bond will be generated between oxygen and hydrogen. Nitrogen as it is. Now this bond will be a dative bond. In this condition, oxygen will get a plus 1 charge because it is giving 1 electron completely toward hydrogen for bond formation. Hydrogen don't have electron for bond formation. In this condition, the oxygen will become unstable. How it will regain its stability? by breaking bond from nitrogen. And when it will break bond from nitrogen, obviously both electrons will shift toward oxygen because oxygen is more electronegative than nitrogen. This nitrogen already carrying a +1 charge. So when it will break bond from it, a stable product H2O and one more particle will generate. Please check carefully. This nitrogen was carrying already +1 charge because 4 bond it is making, and one more electron is gained by oxygen, so it is losing one more electron, so overall charge will become +2. Now +2 minus 1, +2 minus 1. What is the overall charge of the molecule? NO2 plus 1, +2 minus 1. Just add them. The overall value will be +1. So this is the electrophile which we have, nitronium ion. This nitronium ion is an electrophile which will attack in second step on the benzene ring because it requires electrons. Who require electrons? Nitrogen, which have a vacant orbital. Because oxygen got its electrons, so here vacant orbital will generate. In this vacant orbital, it can adopt electrons. So it will attack on benzene ring. Now let's understand in sulfonation how electrophile is generated. We know in sulfonation which chemical we are using? Concentrated H2SO4. Now what will happen? H2SO4 this is bonding we have in H2SO4. Two particles of H2SO4. One particle will lose H positive and will become HSO4 minus 1. Like if I will open it, so oxygen hydrogen bond is breaking, electrons are shifting toward oxygen side because more electronegative it is. So this H will become H positive and this whole particle will become HO4 and oxygen will carry a -1 charge. So HSO4 -1 it will be. Now this H positive will attack on another molecule of sulfuric acid. And already I said it is an electrophile, want electron, oxygen is ready with lone pair. So it will attack on it and the second molecule will turn itself to this. This oxygen will make dative bond with hydrogen because hydrogen don't have electron for bond formation. Both electrons will be provided by oxygen. So it will carry +1 charge. In this condition, it will become unstable. It will break bond from sulfur. Now next what will happen? Here I am drawing. Bond between oxygen and sulfur will break. Both electrons will shift toward oxygen. H2 will release out. H2 is released out. And this sulfur will become +1 charge particle because one electron is gone with oxygen. Now its positive charge will be satisfied by neighbor oxygen by breaking bond from hydrogen and it will shift electrons here, due to which this acetylation I am rubbing, later we will write. It will release out H positive and oxygen will make second bond with sulfur. So SO3 gas, sulfur trioxide gas will generate. Now this sulfur trioxide gas will work as an electrophile. It will attack on a benzene ring. This is the electrophile we have in sulfonation. Note down. You will say how it will work as an electrophile. Let's quickly check. Because electrophiles have a vacant orbitals to adopt electrons. In this SO3, we are not watching any vacant orbital, but be careful. Such type of electrophiles are known as neutral electrophiles. Normally, they are not looking like an electrophile, but when they need to work as an electrophile, they will. Look how. During reaction time, this pi electron will break and both electrons will shift toward oxygen, due to which, don't you think, this oxygen will become a negatively charged and a vacant orbital will generate on sulfur with a +1 charge. That's it. Vacant orbital is there. This vacant orbital can adopt electrons. So in this fashion, sulfur trioxide can work like an electrophile during reaction. Now halogenation. In halogenation, in first step, how electrophiles are generated? We know what are the conditions required for halogenation. You can use any halogen, chlorine, Cl2, Br2, I2, F2. So I am representing halogens with X. With them, what we need? AlCl3 you can use, or FeBr3 or FeCl3 or even BF3, boron trifluoride we can use, because all they have vacant orbital in central atom. Aluminium have vacant orbital. Now due to vacant orbital, this aluminium have tendency to attract electrons. That's why it is working as Lewis acid. Working as Lewis acid. Now right now it is a non-polar particle. It's a non-polar particle. There is no electrophile because electronegativity of both axes same. Electrons are in center. So it's a non-polar. But in the presence of AlCl3, what will happen? Polarization of particle will happen. Due to this vacant orbital, electrons will little bit shifted toward one x and they will be delivered toward aluminium like this. Due to which, here we will have a charge separation. One x who is losing electron will become partial positive and another x bond breakage will start. Will start making bond with AlCl3, due to which bond it will be? It will be a dative bond. This x is providing both electrons in a vacant orbital, so it will be a vacant, this is dative bond, and aluminium is getting extra electron. One electron x will keep with itself and one electron it will transfer toward aluminium. So aluminium is getting one extra electron, that's why -1 charge will develop over here. Look at this. This x is now positive. Positive particles are electrophile. In this fashion, electrophiles are generated in halogenation. Now let's go for alkylation. Alkylation condition, reactants, chemicals I already told to you. Alkylation. And in alkylation, which alkylation we are going to do here? Methylation. Means methyl group we have to add. A CH3, I will write CH3 like this. X. Again AlCl3, FeCl3, FeBr3, BF3 you can use because they have vacant orbital on their central atom. Now you know what will happen? Same. This is a vacant orbital, require electrons. Who can provide electron? X. X will transfer these electrons toward aluminium, due to which carbon particle will become positive. Vacant orbital will generate on it. Directly I am going to draw it. Complete bond breakage I am showing. X will break bond from carbon and will shift electrons toward aluminium. So AlCl4 with a negative charge will generate over there. And this particle is an electrophile. It will attack on benzene ring for electrons. Last is acetylation. For acetylation, chemical requirements are CH3COCl, acetyl chloride, and again that AlCl3 or FeCl3, they all are Lewis base. So what they will do? Same what they were doing. Vacant orbital, electrons are there, electrons are going in vacant orbital, due to which this carbon will become vacant orbital, positively charged particle, acylium ion, and AlCl3 will become AlCl4 -1. I already told you how -1 is generating over there. This Cl is providing electron to aluminium, so this negative charge, this complete -1 is on aluminium. In this fashion, electrophiles are generated. Acetylation, acylium ion will generate, it will attack on benzene ring in second step. Now let's go for the second step. Now second step is common for all. This was the first step. Let's go for the second step. What was the second step of this mechanism? Second step was attack of electrophiles on benzene ring. In first step, electrophiles are generated, which I will represent through E, positive. In haloarene, benzene ring is there, X is there. Now, on what position electrophile will attack? Already we have discussed ortho and para positions are available here. Reason, due to resonance, mostly always electrons are present on ortho and para positions. Please check previous videos. So, I'm going to start the step second. Electrophile will attack, let's attack on ortho. Para, you can try by yourself. I am doing with ortho. Let's attack electrophile on ortho position. Now check what will happen. We know electrophile have a vacant orbital. It don't have electrons for the bond formation. And for bond formation, 2 electrons are required. So who will provide electrons? This carbon. The responsibility will be of this carbon. What this carbon will do? It will bring both pi electrons toward itself and will use these 2 electrons to make bond with E. Let's do it. One hydrogen is already there. So when these pi electrons will be shifted toward carbon and will use to make bond with E, such type of condition will generate X as it is. Now because this carbon is losing its electron, so it will become vacant orbital positive particle, carbocation. What was the name of second step? Second name was generation of carbocation. In this fashion, carbocation will generate. Electrophile will attack on ortho position. Carbon will shift pi electrons toward itself for the bond formation with E, due to which neighbor carbon will become positively charged. Now, next point, this carbocation is stabilized by resonance also. Watch. This is X as it is. E is joined over here, H is there. A positive charge is there. Pi electrons are available. Look how you will draw resonance of this. This positive charge, please understand this is a vacant orbital. Every time I will not draw, just I will draw positive. You will understand it's a vacant orbital over there. Now that vacant orbital will be satisfied by these pi electrons. They will shift here and will make bond with that vacant orbital, due to which next condition will become this. Bond will generate here. Check properly. These electrons are getting shifted here. Vacant orbital was there. So vacant orbital, these 2 electrons will make bond. So bond will generate over here. Now because this carbon, watch carefully, this carbon is losing one of its electron. So now this carbon will become positive charge and vacant orbital will generate on it. Rest part as it is. This one. Now again, this vacant orbital, the positive charge will be satisfied by the neighbor carbon. Again will be shifted like this. The next structure will be, now pi bond will generate here and vacant orbital will generate on this carbon, because this carbon is losing its electron, so its orbital will become vacant with a positive charge. E and H as it is, X is as it is. Now can we move further? No, because pi electrons are not there. If we have to satisfy this vacant orbital, the reverse cycle will start again and you will go back. So these are the 3 resonating structures we have for carbocation, and these 3 resonating structures are providing stability to the carbocation. Because with this, the positive charge is decreased. Watch here. Here was the positive charge. In next structure, we don't have positive charge. So positive charge is decreased. Here we don't have positive. Next we have positive. Next we don't have positive. So positive charge is continuously moving, so due to which the carbocation is stabilized. Now overall, if I draw average structure of it, average structure means you have to check from what position to what position positive charge is moving. I believe from this carbon to this carbon the positive charge was moving. So these dots are showing movement of positive charge, and here I will write positive. Positive means the movement of positive charge from here to this carbon. So this is the hybrid structure of these 3 resonating structures. In this fashion, second step is happening, and this is slow step, rate determining step. Now last step, what will happen next? At last there will be a loss of proton, H positive ion. In third step, what we got? We got this. This one. Is it a final product? No, it cannot be a final product because it's an unstable particle. Because positive charge is there, benzene ring is losing its aromatic character. Aromatic character means 6 pi electrons are not there. Now, how stability can be regained? Look, during nitration, HSO4 negative was generated. During sulfonation, HSO4 negative was generated with in nitration NO2 positive was the electrophile. In sulfonation SO3 was electrophile. And in alkylation, halogenation, acetylation AlCl4 negative was generated and rest were electrophiles. Now here we have a role of these particles which are nucleophiles. What they are? They are nucleophiles. What are nucleophiles? Which attack on positive particle. Now, watch carefully. This carbon made this benzene ring unstable because it shifted pi electrons and provided to E, due to which carbocation was generated. Now, this carbon will help it to regain the stability. How? It will break bond from the hydrogen, this hydrogen. Obviously, both electrons will go toward carbon because carbon is more electronegative than hydrogen, and give these electrons back to benzene ring. And this hydrogen will release out as H positive, and that H positive will be attacked by nucleophiles which were generated in first step along with electrophile like HSO4 negative, AlCl4 negative, these particles. These particles will absorb H positive with it, and what they will do? Quickly let's check. If HSO4 negative will combine with H positive, it will again give you H2SO4 particle. If AlCl4 negative combines with H positive, it will give you AlCl3 plus HCl. So your AlCl3 will regenerated again like initially it was. Now, what is happening with H positive? It's not so concerning part. The main concerning part is this. A carbon will break bond from hydrogen, that H positive will be combined with nucleophile. Okay, that's we have understood. After this, what it is doing? It is shifting electrons back toward benzene ring. So benzene ring will get its 6 pi electrons back, and E will be there, and H will eliminate out as H positive. So finally, E has substituted our H, and H is eliminated out as H positive. One stronger electrophile has substituted weaker electrophile. That's it. This is the end of the mechanism that we call electrophilic substitution reaction mechanism. 3-step mechanism. Understand every step and make it clear. Thank you very much for watching the video.